morning, everyone. I am M. Venkatesh, working as an assistant professor in Tribly Department in PBR Viswadaya Institute of Technology and Science. So, in this video, we learn about the types of generators, types of DC generators. But actually, a DC generator as a symbolic representation is like this, as a symbolic representation of like this. So here we can see the symbolic representation of DC generator. So actually here the generator can represent in circle shape. So the G denoted by a letter, that is a generator, and the arrow indicates in which direction we have induced the EMF. So that's why this direction we are getting the induced EMF, that is the E. And A1, A2 terminals are the armature terminals, and F1, F2 terminals are the field terminals. So here PM is nothing but prime mover. So what is the importance of prime mover means? We need to provide the mechanical energy to the generator. Okay, so in this generator, they produce the magnetic field. So due to the magnetic field, they can energize the field winding. So that is initially energize the field winding, then produce the magnetic field. So here energization of field winding means how to energize the field winding? We are providing the supply to give the supply to the field winding. So that process is called excitation. So here we are applying the supply to the field winding. We are applying the supply to the field winding. So that is nothing but methods of excitation. Methods of excitation. So methods of excitation means methods of giving the supply. Methods of supply to the field winding. Methods of supply to the field winding. So how to give the supply to the field winding. So that is called methods of excitation. So based upon these methods of excitation, the DC generators are classified into two types. One is separately excited DC generators and self-excited DC generator. So here the separately excited DC generator means we are providing the supply. We are providing the supply to the field as separately. As separately. So that is called separately excited DC generator. Coming to next, self-excited DC generator means so initially any generator they can produce the generator voltage. That generated voltage is useful to energize the field. Energize the field. That means what? Itself it excites the field winding. So that's why it is called self-excited DC generator. So that's why. So here how to connect the armature winding to the field winding. So based upon this energization, that means what self-excitation means. So we are giving the supply itself. Itself means we are connecting the armature to the field winding. So here we are getting the induced voltage. That voltage can energize the field winding. That voltage excites the field winding. So that process is called self-excitation. So in this process, the armature connect to the field. So that's why how to connect the armature in electrically, in which way we are connecting the armature to the field. So based upon this type of connection, armature to field winding connection, it is again classified into three types. Again classified into DC generators or DC shunt generators and DC series generators and DC compound generators. So here that is a based on the armature connection, armature winding to field connection. So that's why the self-excited DC generators are classified into DC shunt generators, DC series generators, DC compound generators. So in this DC compound generators means the field it compound means what? Combination of two. So combination of series and shunt connections. So based upon these connections, the DC compound generators are again classified into two types. One is short shunt compound generators and long shunt compound generators. Function compound generators. So these are the types of DC generators. Okay, so let us see how individual. So how we can provide the supply, what is the current and voltage equations, what is the induced EMF equation in each and every type of generators. Okay, so then we can go for first one. So we can go for first. So in this, before we are going to these classifications, we can see some important terms. That means some denotional letters. So what are they? So here you can see IA. So IA. So IA means what? It is a current. I means current. So A means armature. That's why it's a armature current. Similarly, V suffix A. So voltage at armature. That's why it is a armature voltage. I suffix L is the load current and V is the terminal voltage. I suffix SE. SE means series. So ISC, series field current, and RSE is series field resistance. Similarly, E suffix G, induced EMF. That is a generated induced EMF. RA, it is the armature resistance. So armature resistance. IF, F for field. So that is the field current. RF, R for resistor. F for field resistance. So here RSH, SH means shunt field resistance. ISH is the shunt field current. These are the some important terms. That means just terms. So for identifying the currents, for denotion of currents in the circuit. So let us see the first separately excited DC generator. So this is the figure of separately excited DC generator. So in this figure, you can observe, so the circle shape, this is the generator. In this generator, we have getting the, you observe the EG. So terms EG, RA, IA, A and AA. So here A and AA is nothing but armature terminals. And these two plus and minus are the brushes. These two are plus and minus brushes. And EG means generated induced EMF. RA means it is armature resistance. IA means armature current. And here we get IL. IL means load current or line current. And here we are connecting a voltage, taking a voltage that is across the load, voltage across the load. Okay, so that V is nothing but voltage across the load, that is a terminal voltage. And see here Z and ZZ, that is the field winding. And then here I1 is nothing but IF, field current. So here we are applying the supply. That means we are giving the supply to the field as separately. That means a separate part. Armature is a one part, field is a another part. That's why this type of connection is called separately excited DC generator. When we are providing the supply to the field, they can allowing the current, they can produce some flux. That flux passing through the air gap, and then armature can rotating part. So this armature cut the magnetic flux lines. Due to the Faraday's law, we are getting the EMF. That EMF is EG. That EMF is EG. And then when EMF is induced, they have some current, that is a IA is developed. That IA armature current passing through the line. So this line. So in this line, IA passing through the line and it is entered to the load. That's why in this line, IL means load current. Load current is equals to the armature current here. So load current is equals to armature. Why? The both are in a single line. Okay. And coming to apply the KVL of this secondly. That means this loop. Apply the KVL of this loop. So here, so what is the KVL? The algebraic sum of all voltage drops in the loop is equals to 0. So that's why here we have the term, that is one drop, that is the armature drop, that is the IA into RA. And here we have a voltage, that is the EG, that is the induced voltage. It is in the plus sign. And here we have the armature drop, that is the internal resistance, armature resistance, that is the RA. So and then load. So that's why the EMF equation EG equals to V plus IA RA. That is the voltage equation of the DC separately excited DC generator. That is a V plus IA RA. and how much power generated in the generator. So how much power generated in the generator? What is the power? Power is simply product of voltage and currents. So that's why. So here, what is the voltage induced in the generator? That is a generator induced voltage as EG. That is the EMF. And what is the current in the armature? That is a generator. That is a IA. So that's a voltage into current. That's why EG into IA. That is nothing but power generation. And next one, power delivered. So where we are getting the deliver the power at the load side. So that's why the delivering power at the load side. So what is the voltage at load? That is V. What is the current at load? I. That means V into I. So these are the equations of DC separately excited DC generators. Separately excited DC generator. Okay, so now we can see the next self-excited DC generators. In the self-excited DC generators, the first one is DC shunt generators. So shunt means parallel. So in the self-excited DC generators, so armature, how to connect the armature winding to field winding. So based upon that, it is classified into shunt, series, and common. So similarly here, the field winding means Z and ZZ, and armature means A and AA. So see here, so armature terminals A and AA. So these two armature connection connected parallel to the Z and ZZ. That is a field wind. That's why this generator is called shunt generator. This field winding energized by the current from the armature. That means you can see here. So initially the induced EMF, that is the EG. So here IA amount of current. So that current passing to the line and it entered to the junction. That current divides in the two. That is a one current is passing to the field, another current passing to the load. So here ISH is nothing but shunt field current and IL is nothing but load current. IL is nothing but load current. IA is nothing but armature current. So here, so initially there is no supply. That means initially there is no supply means there is no current. But due to the residual magnetism property, so without any supply to the generator, it having some minimum flux, minimum current passing to the winding. So that is called separate residual magnetism. That is called residual magnetism. That means in practically there is no supply means generator is not working. But without any current also they have some flux passing to the windings. So due to that flux they can develop some minimum amount of current in the generators. So that current can energize the field winding. So then only it can use the that is increase the flux lines in the circuit. Okay, so that's why here the armature current can energize the field. That means in itself it is excited. So that's why it is a self-excitation mission. So here the field connected parallel to the armature terminals. That's why it is a parallel connection. That's why shunt field generator. So shunt field generator is called DC shunt generators. In this, initially the current is IA. That IA enter to this node can divides into two. That's why IA equals to IL plus ISH. ISH plus IL. And the current passing through this field is ISH. And what is the resistance of field? That is a RSH. So field as RSH. So in the parallel connection of any nodes in the parallel branches, the voltage is same. That's why in the parallel branches the voltage is same. That's why here the load voltage as V. So that means this load voltage, the terminal voltage is same in the branch of field, shunt field. That's why the current ISH equals to voltage V by RSH. And then what is the induced EMF equation in the shunt field? So what is the induced EMF equation? That is EZ equals to, you can apply that KVL here. You can take the one loop. So that means IA into RA plus V. So V plus IA RA. But IA equals to what? IL plus ISH here. Okay. And how much power generated in the generator? that is EZ into IA. How much power delivered from the load to the load? So that is V into IL. Okay, this is the shunt generator. Coming to C, DC series generator. So in this figure, you can see here in this figure. So the field winding connected in series to the armature. Field winding. So this is the field winding Y and YY or Z and ZZ. Okay. So this field winding in series to the armature. Okay. So in series connection, and then the current passing to the load. So series connection. That's why this generator is called DC series generators. This generator is called DC series generators. Okay. So here similarly the generator current, that is a IA, is the armature current passing from the armature and enter to the series field, and this series field may excite. So that's why it is a self-excited machine. Okay, so this series connection, the current is same throughout the circuit. That's why IA equals to ISE, that is a series field current. That means what current enter to the field, that is ISE, and IL as the same. Okay, and then the resistances. So here RA is there and here RSE is there. That means what? RA plus RSE in series connection. Okay, V is nothing but terminal voltage. What is the voltage equation of DC series generator? That is EZ equals to, we can apply the KVL. So V plus IA into RA plus IA into ISE into RSE. Okay, see here. So here ISE is nothing but series field current, RSE is nothing but series field resistance. So in this series connection, IA equals to IL equals to ISE. That means currents are same, and that voltage equation V plus IA into RA, that is the internal resistance, that is the internal armature voltage drop, plus the series field voltage drop. Okay, ISC into RSC. And power generated, that is nothing but EC into IA. Load power delivered, that is V into IL. Okay, this is the DC series generator. Okay, so next we can see that DC compound generator. So in the DC compound generator, we have two field windings. That is the field windings or two field windings. So it is the combination of series and shunt field windings. So how it can connect? See here in these two figures. So in this figure, the series field winding and shunt field winding combination. That's why it is a compound generator. That's why it is a compound generator. Similarly here in this figure also series and shunt field winding. That's why it is a compound generator. So in this, so one is DC short shunt compound generator. Short shunt compound generator means the field winding, shunt field winding connected across. Okay, so in the DC compound generators, so connected shunt field across the armature terminals. That's why it is a short shunt compound generator. Coming to in this figure, the shunt field connect over the series field and armature to connect total series and armature. That is a long shunt compound generator. In this, you can observe IA is entered to the first figure in the short shunt compound generator. The initial current from the armature is IA. IA entered to the node. That is what that current entered to the node and divides into two currents. One current is from passing through the load. One current is passing through the shunt field. Another current is passing through the series field. One is ISH that is a shunt field current, and another current is ISC. That's why IA equals to ISH plus ISC. IA equals to ISH plus ISC. IA equals to ISH plus ISC, and ISE equals to IL. ISE equals to IL, and ISH is nothing but terminal voltage, that is a V, voltage across the load terminals, voltage across the load terminals by this RSH. But here a series field resistance is there. That means what is the voltage across the armature? The voltage across these two terminals, that is IA terminals. So that means ISC RSC is a one voltage drop and another voltage drop is V. That's why the voltage across, so the voltage across the which terminals? So the voltage across here in this point 2 and in this point. So that means the voltage across these 2 points is nothing but the voltage across the shunt field. So that is that is V. So that means these 2 points is equals to these 2 points. That's why the current passing to the field ISH equals to voltage by resistor. That voltage is taken as simply what? That voltage is taken as simply what? So V plus ISC into RSC. Coming to here in this, so the shunt field is connected over the armature and series field. So in this series field connection, IA equals to current passing to the series field also same current, that is a series connection. IA equals to ISC. That ISC enter to the node. This is the node. So in this node, what the current is divides. One is ISH, another one is IL. So what is the voltage across the points of these two? Voltage across these 2 points. So voltage across these 2 points. Voltage across these 2 points is what? V. That means the voltage across these 2 points is what? V. That means voltage across the shunt field also, same. That means voltage across shunt field as same, that is V. What is the current? I equals to V by R. So that means V by RSH. And what is the entering current here? IA equals to ISC. So that means what? So IA equals to ISC. So IA equals to ISC. Then ISC equals to what? IL plus ISH. IA equals to ISC, that equals to IL plus ISH. And ISH equals to what? V by RSH. So we can see what is the voltage equation of short shunt and long shunt equations. So in the voltage equations, so there we get simply, so you can see that short shunt. So what is the voltage? EG equals to IA. That means what is the current here? IL. So that means ISC into RSC plus V plus IA RA. That is nothing but what? EG. Okay, so we can see here. So V plus IA RA plus ISC RSC. If we consider the brush drop, so you can simply add. So, but normally we can ignore the brush drops. Okay. Similarly, long shunt compound generator. In the long shunt compound generator also, the voltage equations EG equals to V plus IA. So see here. So EG equals to V plus IA RA plus ISC RSC plus brush drop. Why means, so here it is a simply apply the KVL of the loop and write the voltage equation. And power generator of the generator, in the generator is same for all. So that is a EG into IA and power delivered as V into IR. This is the compound generators. Okay. In next class, we will discuss some problems on these different type of DC generators. Okay. Thank you.